Okay, I want to look at another example of using long division to integrate a function. Um, so in this example, um, and this is where long division is useful, notice you have what's called a rational expression, right? So that's one polynomial divided by another polynomial. And often when you're trying to find the antiderivative of a rational expression, um, this process of long division can be useful combined with our knowledge of um, natural logs. And when long division is going to apply, it doesn't apply in every case, but when it does work, it'll work when the degree of the numerator, remember a rational expression is a polynomial divided by a polynomial, right? So polynomials have degrees. So long division will help you with anti-differentiation. When you have when you have the degree of the numerator, the top polynomial in the rational expression, at least as large as the degree of the denominator. So here we see in the numerator, this is degree 2, right? Because the highest power of the unknown in this polynomial expression is 2. And in the bottom, we have a linear polynomial. This is degree 1 because the highest power of x here in the denominator is 1. And of course, 2 is bigger than 1. So this is a case where uh, a long division might help us. Now, I want to point out that you don't necessarily have to use long division um, in this in problems in finding antiderivatives of rational expressions like this one, because sometimes some other simplification techniques will work that are easier. Let me change this problem slightly. And this antiderivative actually is easier to find. So notice what I did is I just changed the x plus 2 to x minus 2. So still we have a degree 2 polynomial here divided by a degree 1 polynomial. But I want to point out that in this problem, you can find the antiderivative much more easily simply by reducing the rational expression. So notice that numerator in this rational expression is going to factor. So it factors as x minus 2 times x minus 1. And of course, we have that divided by x minus 2. And so notice in this case, the x minus 2's will divide out. And so you'll just get left with the antiderivative of x minus 1. And that now is a very easy antiderivative to calculate, right? You can simply use the power rule here, apply it to both terms, and you can see that the antiderivative is going to be x squared over 2 minus x, and then of course plus the arbitrary constant. So we don't need long division to help us with the antiderivative of this rational expression. But we were just fortunate there because it turned out that this rational expression reduces by factoring and then dividing out common factors. Now, unfortunately, of course, we can still factor the numerator in this rational expression because it's the same as it was here, right? So this numerator will factor as I mentioned, x minus 2 times x minus 1, but that doesn't really help us reduce or simplify the integrand in this problem because, of course, you can't divide out the denominator, right? All right, so here's a case where we're going to apply long division. All right, so let's carry out that long division. I'm going to rewrite the integrand by using long division. So let me give myself a little bit of room here for carrying out the long division. This isn't a terrible long division problem, but we're going to divide x plus 2 into x squared minus 3x plus 2. All right, so I know you've done long division with polynomials before. You may be rusty with it because it's not something we do every day. But after you've done a couple of examples, you'll get familiar with carrying out the long division again. It's really pretty simple. So we're going to start by dividing the leading term in the divisor by the leading term into the leading term in the dividend. This is called the divisor. That's what you're dividing by. This quantity that you're dividing into is called the dividend, right? So we're going to start with the leading term in the divisor, and we're going to divide it into the leading term in the dividend. So I'm going to divide x into x squared, and of course, when you divide x squared by x, you just get x. If you don't see that, of course, you can write that down off to the side here. I'm going to take x squared and divide it by x, right? Divide x into x squared, and of course, x squared over x reduces to x. Now, when I write down the x, it's going to make my life much less prone to error if I keep my like terms lined up. So I'm going to write this x over the 3x term, right? Because these terms have the same degree. These are like terms. All right, now let's carry out this first step. Let's finish carrying out this first step of the long division. So I'm going to multiply the x back through x plus 2, right? So x times x is x squared, and then x times 2, of course, is 2x. And now we're going to subtract. Now, here we're subtracting polynomials, so it's a little bit easier when you're subtracting polynomials to think of this as changing the terms in your polynomials and then adding. So I'm going to make this plus x squared a minus x squared, and I'm going to make this plus into a minus. And now let's add terms. So we get x squared minus x squared added together. Of course, that's going to be 0. And minus 3x minus 2x is minus 5x. Bring down the 2, so I have now minus 5x plus 2. Okay, now we're just going to repeat the process, right? This is long division, so I'm going to divide x into minus 5x. That'll be minus 5, right? Again, if you need to, you can write this down. Off to the side here, you have minus 5x divided by x, and of course that reduces to negative 5. Now let's multiply back through. So minus 5 times x is minus 5x, and minus 5 times positive 2 is negative 10. Be careful with the signs now. They're not difficult, but you do have to not be sloppy here, right, or not go too fast. Sometimes I do that also. So let's change the signs now and add, because that's the same as subtraction. So I'm going to make this minus a plus, and I'm going to make this minus also a plus. And now let's add. Minus 5x plus 5x is 0, of course, and 2 plus 10 is 12. This is where we stop the long division now, because the degree of my remainder here is 0. This is a constant. Constants have degree 0. And, of course, the divisor has degree 1. X plus 2 is degree 1. Degree 0 is less than degree 1, so we know we're going to terminate the process now. All right, now we haven't done any integration yet, right? We just carried out the long division. So we can rewrite the x squared minus 3x plus 2 over x plus 2. We want to rewrite that as x minus 5, because that's the quotient, right? And then we take the remainder and divide that by the original dividend. That's the same as the original rational expression. So I claim that x squared minus 3x plus 2 over x plus 2, that's the same as x minus 5 plus 12 over x plus 2. I wrote down 12 there because I was getting carried away, but that's x plus 2, right? Take the remainder and divide it by the original divisor. Now we're going to try to carry out the integration, but looking at the integrand written in this form. And this actually allows us now to carry out the integration, because we can now integrate term by term. So I have the antiderivative of x minus the antiderivative of 5. Let me be sure to write my dx's here. So I have the antiderivative of x dx minus the antiderivative of 5 dx, and then plus the antiderivative of 12 over x plus 2. And these first two antiderivatives are so easy to find, you can just use the power rule in both cases. So the antiderivative of x, of course, is x squared over 2. The antiderivative of 5 is 5x. And now for that last antiderivative, first let's factor out this 12 in front of the integral sign. So remember, you can factor a constant in front of an integral sign. It's not a variable, but a constant. So I can write this as 12 times the antiderivative of 1 over x plus 2. And now we can apply our knowledge of natural logs, right, to integrate 1 over x plus 2, because that is going to be just the natural log of the absolute value of x plus 2. Now, why is that? Because remember, when you have an expression like x plus 2 divided into its derivative, and what's the derivative of x plus 2? Of course, it's 1. So you have an expression divided into its derivative. You know that always integrates as natural log of the absolute value of the expression. Of course, we factored the 12 out earlier, right? So that's still going to be there. And there's your final antiderivative. So see, long division there really makes finding the antiderivative of this rational expression really quite easy, right?